So here's kind of a neat application for solving right triangles. We have a person, a 6-foot tall person, who's standing on a bridge, and this person observes a boat traveling toward the bridge. So the bridge is spanning a river apparently. The boat traveling toward the bridge is traveling at 12 miles per hour. The angle of depression, now angle of depression just means the angle down from the horizontal, is 5 degrees 26 minutes. So the observer is viewing the boat at an angle down from the horizontal. I can draw that in here. This angle down from horizontal is 5 degrees 26 minutes. After 30 seconds, so the boat is traveling for 30 seconds, the angle of depression changes to 6 degrees 47 minutes. That would be the angle coming down to this second observation. Okay. How tall then is the bridge? It's weird, but you can actually find that value, the height of the bridge, from those 2 pieces of information, or 3 pieces of information, I guess. The 2 angles and the amount of time with the speed, so that ends up being your distance. Okay. So from that, it doesn't really appear that there's a whole lot of right triangles up here, right? This is a right triangle application problem. However, I can sketch in a right triangle because I'm ultimately looking for the height of the bridge. And so the height, if I drop down a perpendicular line here, the height of the bridge, that gives me right triangles. Okay, so hopefully you can kind of see this on the diagram. All right, so I'm creating right triangles here in the diagram. Okay, so what we have then, we have these 2 angles of depression. Currently, I don't know any of the angles of the triangles except for the right angle here at the base of the bridge, or beneath the bridge. However, the angles in the triangles can be found because we know that if you cut 2 parallel lines with a transversal, alternate interior angles are congruent. Well, notice I have 2 parallel horizontal lines here, and they're cut by 2 different transversals, each of those lines of sight. The first one has alternate interior angles, so this the 5 degrees 26 minute angle here coming down is the same as the angle here in my triangle, because they're alternate interior angles. Okay, so I'm gonna maybe color these or circle them in blue. So this 5 degrees 26 minutes is going to be the angle in here. Now I'm just going to shade this angle in blue because I don't want to, it's getting a little crowded to try to write that in. Now in green, for the same argument, I would argue that the angle here in the smaller triangle is 6 degrees 47 minutes. Because again, it's the alternate interior angle in the parallel line case there. So this angle down here is going to be 6 degrees 47 minutes. Okay, so I do know some of the angles in our triangle. What I don't know are any of the sides. I know none of the sides at this point. What I want to do is find the height of the bridge. So that's definitely going to remain unknown. The hypotenuse of each of these triangles is going to be very difficult to find, but there is one thing that I can find, and it is the distance between the 2 observations, or the distance between the location of the boat at the 2 observations. We know it's traveling toward the bridge at 12 miles per hour, and it's traveling for 30 seconds. So we can find the distance between those 2 points, because distance is equal to rate times time. The problem is that these are all in very different units, right? I've got seconds here, I've got miles per hour here. Ultimately, this bridge is not going to be measured in miles, it's going to be measured in feet, right? How many feet it is up, not how many miles it is up. So I really want to get everything in feet because feet makes more sense here. So I would like to find, let's get rid of this. So I would like to find this distance in feet. That would be preferred so that I can get the height in feet. To do that, I know that, again, distance is equal to rate times time. The rate in this case, 12 miles per hour, I want to convert miles and hours into feet and seconds so that I can apply this time of seconds and change everything to feet. So I'm going to use what we call the unit, unit analysis. We did this, maybe we haven't done this really yet. We've done this a little bit, I think, in chapter 1, but a little bit of unit analysis. And so I'm going to take the 12 miles, and remember, unit analysis, I do this technique where I do a whole bunch of fractions next to each other and multiply them together. We got 12 miles in 1 hour. Okay, 12 miles per hour. I want to change the hours into seconds. Well, I know that there are, let's see, in 1 hour, there are 60 minutes. And in 1 minute, there are 60 seconds. So that converts this, if I cancel out my hours and my minutes, remember, we talked about unit canceling when we did unit analysis in some previous videos. This would give me miles per second. But again, I want to get the miles converted into feet. You may know that there are 5,280 feet per mile. So I would say I want the miles on the bottom. So 1 mile makes, what did I say, 5,280 feet, okay? So I get all of that, and then at the end, I still have to, so that's my rate. That's just converting the rate. Then I have to multiply by the time. Well, the time is 30 seconds. So I would multiply that by 30 seconds. I don't have a denominator there. There's no per. There's nothing it's equal to, so I'm going to leave it there. If I cancel out the corresponding units, the miles cancel out, the seconds cancel out, and all I will be left with is feet. So that would give me a distance in feet along the bottom, okay? So a long unit analysis here. If I go through and calculate this, I could just punch it in my calculator, multiply everything on top, and then divide by everything on the bottom. The bottom has 60 times 60, which is 3,600. So what I could do is multiply everything on top and divide by 3,600, which is what I'm going to do on the calculator here. So I'm going to go 12 times 5280 times 30, hit enter, and divide that by 3,600. And I get 528 feet, okay? So this distance is 528 feet when I calculate that. Works out really nicely. Okay, so 528 feet, and now you may think, well, that was maybe pointless because I have no idea. I still don't know this other side of a right triangle. I don't know any sides of the right triangle. I know the difference between the two sides, bottom sides of the two right triangles. So let me redraw a little bit of this diagram just so you can see the two triangles a little bit more clearly. Okay, so I decided I needed a little bit more space, so I got rid of some of the work here, and I'm going to redraw the two triangles, set them aside, and then work with them individually. So the first one we'll deal with is the one that I have the angle in green. I'll use a green marker. And so my triangle is going to have we know it has a 90-degree angle. the bottom right angle is this 6 degrees 47 minutes. And I don't really know anything else about that triangle. Okay, oh, I do know one thing. I'm going to give a variable to the height there. Okay, so the height to the bridge is h. Now I understand that there's, we're going to have to account for the height of the person because these observations are coming from their eyes and they're 6 foot tall. So essentially that's going to subtract 6 feet off of the answer. We'll deal with that at the end. Okay, so just for right now, we're going to include that whole height up to the observer's eyes. Now the second triangle, the one that I did in blue up here, let's extend this out. A little bit longer triangle. And it has a right angle. It has the same h for the height, that's the same variable. And the lower right angle is going to be the 5 degrees 26 minutes. Okay, so I've got my 2 angle measures in there. Now again, I don't know any of the other sides precisely, but I do know something about this horizontal side, that it's got a 528 foot portion to it. Okay, so there's a portion here that is 528 feet. What I don't know is the remaining amount, but that remaining amount is the horizontal side on the smaller triangle. And so I could give it a name and it would be the same on both triangles. So for the purposes of this example, I'm just going to call it, I'm going to throw a dummy variable in there. Maybe I'll throw the letter D in there for dummy variable. I don't know. So I'll put a D right there. And that translates to the remaining portion of that horizontal side. So I've got 2 D's, 2 dummy variables there, okay? Now, in each of these triangles, you might notice that we have a lower right angle, we have a vertical side, which is the opposite, and we have the horizontal side, which is the adjacent. And so if you want to relate an angle to the opposite and the adjacent, you use tangent, okay, the tangent function. So in each of these triangles, I could set up an equation involving the tangent function. The first one, I would say that the tangent of the angle 6 degrees 47 minutes is equal to the opposite hypotenuse over, or opposite h over the adjacent, which is the dummy variable, so h over d. And then in the other triangle, I would set up the same sort of tangent relationship, and I would have the, I want to do that in blue. I would have the tangent of 5 degrees 26 minutes equal to the opposite side over the adjacent side. Now the adjacent side is just the sum of D and 528, so it's D plus 528. Okay, so these two equations can both be solved. They both have fractions in them, so we can eliminate the fraction by multiplying both sides by denominators. That'll be the next step. But the reason I want to do that is because I have this common h, and if I can solve each equation for h and then set them equal to each other, set the h as equal, then I'll have an equation that I can solve that will only have d in it, okay? So this first equation, I'm going to multiply both sides by d, and that will cancel out on the right, on the right side, and that will leave me with an equation. I'm going to set it off to the far side here. It's going to be the equation h equals, that's all that's left on the right side. I'm switching sides here. D times the tangent of 6 degrees 47 minutes. Okay. The second equation, I'm going to multiply both sides by the denominator, which is d plus 528. So multiply by d plus 528 on the right, and do the same on the left, d plus 528. All right, multiplying both sides. Now it cancels on the right, and so I'm going to be left with the equation h equals d plus 528 times the tangent of 5 degrees 26 minutes. Okay, so now I have two equations. They each are solved for h. If two things are equal to h, then they must be equal to each other. Okay, so at this point, I'm going to do a little bit of erasing here. Get rid of this setup. And now I can solve the corresponding equation, right? So if these two things are equal to h, then they're equal to each other, and I can solve them. So I get d, I want this in black marker. So let's see, d times the tangent of 6 degrees 47 minutes is equal to d plus 528 times the tangent 5 degrees 26 minutes. Okay. Well, I will say this is one of the longer and more difficult problems that you'll see. Okay. Now we got to solve for d. Now you could solve this in a variety of different ways. I'm going to make this a little bit simpler by calculating these tangents. Now I know some of you might be thinking, or at least I would be thinking, if I calculate these tangents and round off the decimal, I'm going to create error in the problem, and that's true. I'm going to be willing to just do that right now. We'll keep 4 or 5 decimals here as we go, but just so that you can more easily understand the process of solving the equations, really what I want you to focus on. Okay, so I'm going to calculate these tangents. The first one, now when you calculate degrees and minutes in the tangent, one of the nice ways to do that is to just type in tangent of 6 plus 47 over 60. Remember, 47 minutes is the same as 47 over 60 degrees, or 47 sixtieths. And so if you add those together, you get the total number of degrees. So I would go to the calculator here, and I would simply type in the tangent of, 6 plus 47 over 60. Okay, so and then close the parenthesis. That's what I'd be looking at. Hit enter, and it's about 0.118905, I suppose. 0.1185 or 895. If I round that to 5 decimal places. So let me erase this right here. I get d times 0.11895. All right, I'll round it off to 5 places after the decimal. So yeah, I am introducing some error here. I think in the end, a lot of that error isn't going to be too noticeable. Okay. So here, I'm going to take this tangent on the other side and do the same sort of thing. Tangent of 5 plus 26 over 60. Okay, so I'm going to type that in. I won't show this one, I'll just do it. Tangent of 5 plus 26 divided by 60. And that gives me 0.09511. Okay, again, 5 places after the decimal just to be consistent there. Okay, so now I'm going to distribute, right? I have a plus and a times. I'm going to distribute this decimal into the parentheses. And that gives me D on the left times 0.11895 equals, now here I get D times 0.09511. And then I've got to multiply by 528. Well, I already have this on the calculator with all the decimals, so I'm just going to hit times 528, and that gives me 50.22. I'll just round it off at 2 decimal places. Again, I'm not doing this I'm not taking a lot of care in where I'm rounding these off. If I was really trying to get a precise measurement on this, I would keep more of these decimals, okay? At this point, I might try to get these D terms together. Remember, this is a number times D and a number times D. If I subtract this D term from both sides, I'll keep them just together on one side. So I'm going to put 0.11895, that's this number, minus this coefficient, 0.09511. And that gives me D times 0.02384. Okay, so that's the difference between these two values when I subtract it from both sides. That should equal the 50.22. Well, of course, I've got D times a number equals a number. I divide by this decimal on each side. And so my final D value here is going to be 50.22 divided by this decimal. So I'm going to type that in, 50.22 divided by 0.02384. And I get a D value of 2,106.5. All right, so 2,106.5. Now, I guess I could round that. I'm going to round that off to the nearest foot because that's a distance. I've got everything else rounded in feet here, so, or rounded to the nearest foot. So that's, we'll call that 2,107 feet, okay? Pretty close. Okay, so that's my D value. So now I actually have some information. I know the two horizontal sides now. And so then I can use that to find the height h. So if my distance D is 2107, I can find h by using an inverse tangent again, okay? So let's erase a little bit down here. And I'll get rid of that since I already have it written. And I'm going to use the green marker because I'm dealing with the green triangle. It's just a simpler one to work with. And I know that the tangent of 6 degrees 47 minutes is equal to the opposite over the adjacent, which is now 2107. I'm going to multiply both sides of that by the denominator of 2107. Multiply by 2107 there, multiply by 2107 there, and that will give me the final value of h. Okay, so the 2107s cancel. H equals 2107 times the tangent of 6. Now remember, when I plug this in the calculator, it's going to read 6 plus 47 over 60. And I just put that in the calculator. I should get my final height. So I'll go ahead and show you how that types in. So that's 2107 tangent of 6 plus 47 over 60. All right, so hopefully that looks good. Right? Something else. Yeah. Yep. So 2107, I'll scroll it back to the beginning. 2107 tangent of 6 plus 47 over 60. When I hit enter, I get 250.6 roughly feet. So we'll say H is approximately, again, this is in feet, so maybe I'll just round it off to the nearest foot. We'll say 251 feet. So it's 250.6 or 251 feet roughly, okay? So there's going to be a little error in here, but that's pretty close. So 251 feet looks good. Now that's my total height. Again, I said we had to account for the height of the person. The person is 6 foot tall, so you want the height of the bridge. These, the triangles here include the height of the person because the observation angle comes from eye level. So, so if I take the 6 feet off of this, the height of the bridge is actually going to be 245 feet. Okay, so it's a 245 foot tall bridge. So quite a tall bridge. My diagram is probably not very accurate, but it is quite a tall bridge. Okay. Anyway, there's a lot of trig involved. There's a lot of unit analysis here. There's conversion of degree, minute, second sort of stuff. There's a ton of things in this problem. I thought it was kind of an interesting problem.